Hey, everybody. All right, so this talk, we have three parts. We have a historical definition of infrastructure as code, we have a crash course in graph theory, and then we merge the two together in a very a dive into Terraform's core to see how at the very core of Terraform, we utilize the concepts of graph theory to enable us to have this infrastructure as code tool. So let's get started. So we're going to start with infrastructure as code. I thought it was worthwhile in a talk that has infrastructure as code in the title to give ourselves sort of some time to discuss what infrastructure as code means. From my perspective, I've done a lot of thinking about this, being that I work on an infrastructure as code tool. So for me, in order to define infrastructure as code, I have to tell this a historical story, which is a totally biased and 100% I do not stand by timeline of the chapters of the history of operations engineering. So I'm just going to mix and match things and tell you a story that matches up with this picture in order to ground the definition I'm going to give of infrastructure as code. So in the beginning, it was manual everything. Operations engineering involved physically ordering servers, waiting for servers to come, physically unboxing and racking the servers, installing operating system on the servers, and then managing the services that whatever that computer had to provide. So that means launching processes, writing config files, editing config files, restarting processes. This was the job of the operations engineer, and it was good. People got good at this. People got very opinionated about kernel parameters and spaces versus tabs and config files. You get these people who are good at it, they begin to automate the more rote tasks that they had to do. So you start to see basic automation where you get teams and individuals that are writing scripts to automate the tasks that they have to do every day, server setup, application configuration. And not a whole lot of collaboration at first. It was a bunch of individuals solving a bunch of individual problems. Then you hit the wave of machine virtualization. So now instead of unboxing machines, you can actually run a logical computer on a physical machine, which drastically increases the number of logical servers you have to manage. It also lifts the concept of a server up into software. So at this point, I'm sort of bundling in here an increased amount of collaboration on the automation that we use to set up our infrastructure. So you start to see configuration management tooling. Folks are sharing the solutions that they have to bootstrap machines, and things are getting better. We can deliver things faster because now we're not bound to the delivery time of a physical server and the actual unboxing and racking. So you get the ability to virtualize infrastructure. Inevitably, you have companies that decide, hey, we're going to be really good at virtualizing infrastructure. Turns out it's large companies that became very good at it, and they commoditize infrastructure as a service. This is sort of the era that we're in. And again, it's an increase in lifting up these concepts into software, increasing the ability to automate. So all of your infrastructure is API drivable, and it increases the ability to address it via software and automate it. And then sort of the era that we're in and kind of progressing through is data center as computer, where we abstract away the concept of what a task is, what a resource is, and the actual matching of resources to a given task. And again, increasing the level of automation that we're able to perform. So ostensibly, this is a story of maturity. We get, at each step of the way here, something better. We get new capabilities, we get increased automation, and we get faster delivery. So my question is, why doesn't it feel like it sometimes, especially from an operational perspective? I think you can see this, and if you don't believe me that the progression can feel opposite, I think you have to take a look at the humor in operations engineering. If you don't follow either of these accounts, they're cry laughs a minute. They're always laughs that you cry. But I think it's really interesting to see this idea that we've gained all of this new capability, but there's so much nostalgia in the community for the good old days, for when there were fewer layers of infrastructure management, fewer layers of software, fewer things that could go wrong or things that you don't fully understand. And so I have a theory about this that is that leads us into infrastructure as code, which is first we gain capability, and capability adds complexity. And that's just inherent to gaining a new capability, especially from the perspective of automation. When you gain the ability to drive something with software, the first thing that's going to happen is you're going to get the software that drives it in the most basic way, and the knowledge about how that software works is an increase in complexity. And so the sort of march of progress in our industry is to first gain a capability, then try to deal with the complexity that capability that is inherent in having that capability. So just to kind of give us the idea of the complexity that I'm talking about here, here's an ostensibly basic web application in AWS. Right? This is like a couple of front-end servers behind an ELB, and then some back-end servers that are talking to a database, and an S3 bucket for assets or something like that. But if you zoom out, it's like, wow, that is like, if that's a basic website now, like that's a lot to keep in your head, especially when you think about the fact that each of those services has all sorts of nuance to it, right? Even just in AWS. Not to mention the software that's running on top of them. And so this is the context that I think infrastructure as code is in, which is infrastructure as code is a strategy for managing complexity. This is us looking at the new capabilities and saying, this is so complicated, it makes us cry sometimes. How can we deal with this? How can we move forward? And what we can do is try to look for other times we've solved similar problems. And one of the things that we've been doing with all this new capability is lifting things up into software. So infrastructure is software, and the automation that drives infrastructure is software. It turns out there's a whole industry of people who have been writing software for quite a few years, and they've got complex systems that they have to manage. So you can kind of see, so on the right we have an ER diagram for a relatively complex piece of software. This is Drupal, actually, I think. But you see the link here, where it's like, oh, wait a second. Like a software system is just a set of complexity that needs to be managed somehow. And so if we say, okay, well, how do the folks writing software manage their complexity? They've been doing this for a while, and they've been doing it by capturing the vast majority of that complexity into code. And because when they do that, it enables them to use a bunch of tricks, a bunch of practices that have allowed them to manage the complexity that lives in their software systems. So that's infrastructure as code to me. And you can basically look at all of the practices that we're attempting to borrow from the software development community. Self-testing systems, iterative changes, reproducible artifacts. All of that stuff has links to managing complexity in software systems, and that we're trying to get those benefits in our automatable infrastructure. And so that's exactly where Terraform lives. Terraform is an infrastructure as code tool. It allows you to describe infrastructure in text files. That allows you to get versioning. You can do verification on them. You get all of these benefits. And to me, that's what it means to say that Terraform is infrastructure as code. Cool. So let's talk about graph theory for a minute. Luckily, a crash course in graph theory is pretty simple because graph theory is really easy to learn with a bunch of examples. It looks scary when you do this. When you say graph theory is a division of discrete mathematics, also under combinatorics. And then you get really scared. And in about 2 to 3 minutes, you're going to know most of the basics of graph theory just with a couple of examples. So in graph theory, we have a vertex or a node, interchangeable term. That's just a thing, an abstract thing that can be connected to other things with edges. An edge connects two nodes. This edge is undirected. An edge can be directed as well. So that just means it has a direction. So a graph is just a bunch of nodes and edges. And so this graph has directed edges, so it's a directed graph. This directed graph has a cycle. So you can see a path that starts from one node and then can end back at the same node. And then if a graph does not have any cycles, so if we break the cycle, we can say that the graph is acyclic. So we add that to the directed, we have a directed acyclic graph. That's going to sound familiar to anybody who's used Git. The DAG is at the core of, or many version control systems. So we're going to build up a couple more pieces of vocabulary, then we're going to take a dive into Terraform. So a walk is simply an operation that you perform on a graph where you take each of the nodes and you visit it, which just means that it's an abstract operation, right? You can do whatever you want when you visit. It's just an enumeration over the nodes. We call that a walk. The walk can be in any order. Sometimes the walk follows the edges of the graph. Sometimes it doesn't. Sometimes the walk can visit multiple nodes in the graph in parallel. That's going to become really important for Terraform. So the final sort of operation from graph theory we're going to borrow here is the graph transform. So a graph transform is an operation on the entire graph. It takes a graph as an input, and it produces a modified graph as an output. The modifications that a transform can perform are add edges, remove edges, add nodes, remove nodes, basically anything that you can do to a graph. You can also do nothing. And it's a nice functional operation. Takes one input, has one output. And this is right at the heart of how Terraform uses graph theory. So now you know the basics of graph theory. That's it. Take these examples. They're all very simple, very abstract, very composable. And you start to try to make assertions about them. So the body of work in graph theory is taking these base pieces and then doing research, developing algorithms for answering questions about graphs or modifying graphs or dealing with graphs. Graphs being just a set of nodes with edges. So it's pretty easy to see how this applies to infrastructure, I think. Even just visually, right? Like, you take a look at that AWS picture and you overlay just an abstract graph on top of it, and suddenly you realize, this is probably a good idea. This might be a really useful way to model this. And that's what Terraform does. Okay, so now we've got our basis of infrastructure as code. We've got a crash course in graph theory. Now we're going to dive into the core of Terraform. So I'm going to take us step by step. We're going to start with a higher level map of the overall structure of Terraform. So essentially, Terraform's divided into a core, which we're going to be diving into in a minute. But for this level, there's a core in Terraform that deals with the mechanics of the orchestration engine, and there's a set of providers that are implemented as plugins. And the providers are the things that talk to upstream APIs to actually make changes to infrastructure. So that's where we're interfacing with this programmable infrastructure provided to us by this wave of wonderful automatable tools. The providers are responsible for translating between the cores of verbs that are declarative verbs of diff, apply, and refresh. We'll dive into those a little bit more in a second. Into the more familiar terms of CRUD, which, this is actually not strictly accurate because the providers aren't responsible for this translation by themselves. Terraform includes a library that makes this a lot easier. Paul Stack's going to be talking tomorrow about that library, helper schema, and about implementing your own provider. So that's going to be really fun. So this is the basis of Terraform's core, and let's review some terminology here. So I said diff, apply, refresh. What does that mean? So these, to me, are at the core of Terraform's worldview here. So you have the config, which is user-provided. It's a set of files that describe a target reality. So that's the set of resources and relationships that you want to exist. Terraform records a state after it takes any operation, and that's its view of current reality. And then the diff is just the subtraction between those two, the difference, to get you, so that's the plan to get you there. And so when you present the diff, that's a plan, which is how do I get from the the current state to the target state. And then when you apply, you actually take the steps to move the infrastructure into the target state. So a little vocabulary. This is Terraform's view of the world. So now let's dive into core. So there's three major packages. There's a couple more that I'm ignoring here, but there is a package called Terraform, which does the big show. It actually builds up the graph. There's a couple of helper packages here that are important for this story. Config is responsible for reading and interpreting the files off of disk and getting them into memory and handing them over to the Terraform package. And then the DAG package is the thing that's implementing the graph theoretical concepts. Terraform calls down to the DAG package in order to build up the graph. And so what's really nice here is all of those concepts I said were so abstract and so simple. They are abstract and simple in this package, which makes them really easy to test and to verify that the graph level behavior is correct. So, and this package, so the DAG package rarely gets touched nowadays. It's really interesting. Once upon a time, when I was first ramping on the Terraform project, I would regularly think of a problem as, oh, maybe the graph's not working right. And Mitchell was like, nah, the graph's fine. And he was right 99.9% of the time. Because that's what the separation of concerns gets us, which is the DAG package, the graph concerned package, is very simple, and it's just utilized by Terraform. So how is it utilized by Terraform? So Terraform needs to build a graph. We use this primitive that we got from graph theory that works really nicely for building graphs, a series of graph transforms. And that's exactly what Terraform does to build up the graph. So in reality, it's like a couple of dozen transforms that are involved in the building up of the entire graph. We're going to sort of take a tour of a couple of key ones so you can get the idea of how these things work. I think that'll give a good picture of the way Terraform is interacting with the graph without getting too much into the weeds of the implementation details. So at the very beginning, there's a config transformer. The config transformer is the thing that takes in an empty graph. It's at the beginning of the chain, and it also takes as input the config, as interpreted by a separate package. So it's just a set of structs in memory that says, here is what the user has specified as the incoming configuration. And it produces a graph. So it's going to spit out nodes for the resources it sees. It's going to spit out nodes for the providers it sees. And it's also going to draw relationships between nodes that reference each other. And so if you zoom in, this is what that might look like. So in this case, we have an ELB and an instance, and we're using a separate provider, dnsimple, to get a DNS record for that ELB. Again, same graph. There's several providers. It's all the same graph, the Terraform. So we also have these two provider nodes at the bottom. They're just sort of hanging out there at the moment. The provider transformer is the thing that's responsible for connecting, for discovering the providers being used and connecting them to the provider nodes. So you can see once we run the provider transform, we get new edges. So edges connecting each resource to the provider that it needs. And so again, from the perspective of the graph, what happens when we visit these nodes is totally abstract. It's to the Terraform package that's defining what happens when these nodes are visited. So in this case, the provider nodes are sort of like a config step. So they're the things that like set up an API client, or sometimes they have to do some sort of authentication step. They get ready to speak to the API. And again, we're going to hear more about this tomorrow. From Terraform Core's perspective, that's just a call out to a provider. So Terraform knows that these things are providers. It knows it has to call an API and a plugin, but it's the plugin that implements the details of how that works. So we ran our provider transformer, and we have these links. There's a whole mess of other transformers, including transformers that add logical nodes. So there's a logical node in the graph at the point that any node would be destroyed. There's a transformer that implements the create before destroy lifecycle hook by modifying edges. That one's pretty interesting. But sort of like, logically speaking, they all sort of run in this chain. And they all take the graph in, they make some changes, or they don't, and then they spit the graph back out. At the very end, After all that's done, we get a root transformer. We need a place to start. And if the graph has more than one node without any dependence, we make one, and we call that the root node. And that's where all of our walks are going to start. So so now we have this graph, and again, in real life, it's more complicated. There's destroy nodes. There may have been more modifications done, but at base, this is all there. This is like a very high-level view of an actual Terraform graph. So now we can start the walk. The actual sort of operations Terraform performs require a couple of walks. So we do a walk for validation. We do a walk to figure out if there are any variables that need to ask the user for input. And then plan and apply are both walks. We also do a walk for refresh. So we actually can do multiple operations, but what the walk allows us to do is to do them in the correct order. The other thing that the walk is parallel. So you can see I put the numbers here. So you can see that the root node is processed first. Root is just a no-op. But then the next two nodes are processed at the very same time. Each node is waiting for only its dependencies. And it's going to immediately start execution when its dependencies are met. This is a really wonderful property when you're dealing with cloud APIs that may or may not be performant at any given moment. It allows us to make as much progress as we can, as quickly as we can. And there's also, accepting details like rate limiting and stuff like that. But from a logical perspective, if one branch of the tree requires some very slow APIs, but the other branch doesn't, the other branch is going to make much more progress and get as far as it can before it needs something from the slow branch. It's a really nice property we get, and that logic is all implemented in the DAG package. It's all implemented and tested abstractly, and then we just get this benefit up at the Terraform layer where it's useful. So that leads me into sort of the overview of what we get here. What do we get from the graph? So this is where I feel like it's an interesting link between the concept of infrastructure as code and the way Terraform uses graph theory, which is when you've gained a bunch of capability and you have this complexity that you need to wrangle, I think the thing that you can really look to in order to ground your complexity and in order to ground the problem of managing this complexity is existing knowledge, existing bodies of knowledge. And so what infrastructure as code has done is to say, wait a second, people have been building software and managing the complexity in software for years. We just lifted all of this infrastructure into software. Maybe we can look to the software community for tooling and practices to be able to manage that complexity. I think similarly here, in Terraform, we said, look at this wonderful subfield of mathematics that is very good at modeling the concepts in managing large-scale infrastructure and these dependencies between them. Let's lean on that and use that. So let me break down the benefits that we get from doing that. First, I've talked about this a little bit. We get a really nice separation of concerns, which improves testing and improves reliability in a major way. When you have small, isolated pieces that you can test in isolation, your software is stronger for it. The other thing about sort of the nature of graph theory is it's entirely composable, and it's full of functional operations, which makes Terraform's core itself, each of those graph transforms, can be tested in isolation. Each node visit can be tested in isolation. That gives us a great, just really rich testing environment. So we get a ton of benefits from that. I started gushing about the parallel walk. I can't gush about the parallel walk enough, which is the fact that we can implement this concept down at the graph layer using a bunch of Go routines, and channels. We spin up all the Go routines and connect them together properly and tell them to behave like a parallel walk in this dependency graph, and we get this wonderful property out of it, which is this graph's going to make as much progress as it can. An incredible benefit we get from the graph. Sort of more abstractly from the body of graph research, we have all of these solutions that exist in graph theory that can solve real problems for us. So this is an example that is currently implemented in Terraform, which is our first implementation of the provider transformer. Actually, the current implementation, it still does it. You'll see why in a second. Draws a lot of edges. So basically, every dependency is declared to the superset of all possible dependencies. And so what we ended up with was an incredibly noisy graph that was correct. So all of the dependencies were expressed properly. The graph is going to be walked in a correct order. But reasoning about the graph, especially in debugging scenarios, was very difficult because there were all these extra edges, and it was really hard to determine what order is it really going to be walked in here. You have to sort out all of the extra edges. And what we really wanted was, what is the path that's actually going to be taken for the walk for a walk through this graph? We wanted the minimum graph. Given all of the supersets of dependencies that are being declared here, show me what that looks like. It turns out, graph theory, there is an algorithm that exists, transitive reduction, which basically says, from any node, if I can get to another node via a path, figure out which paths I can delete, such that I have the minimum graph. This is an algorithm that's on the pseudocode's on Wikipedia, and links off to the paper that first introduced it. So all we had to do was implement this algorithm correctly and test that code, drop it into a transformer. So this is our second last transformer now, is a transitive reduction transformer. And it was a beautiful moment because it was so easy. I think there was probably one bug in the algorithm implementation, as we implemented it. But the idea that you can take this graph theoretical concept, implement it down at the graph theory layer, and get this real benefit up at a very useful layer is amazing. So graph theory gives us a solid theoretical grounding for the core of Terraform's architecture. It gives us all of these composable pieces that we can use to construct the more complex behavior that we need in managing infrastructure. It gives us real solutions to existing problems that we have, many of which we've already borrowed. But even more than that, we've really only scratched the surface of what graph theory research has to offer. And so this is what's really exciting to me, is knowing that Terraform is based on a series of graph transforms that build up a DAG. We just have all of this available interesting research that we can use for research's sake, or we can take a given problem that we have and say, I really want this cluster of nodes to be considered together. I want these to. I could just go on and on. You can find me at the conference, and we can rap about what kind of interesting graph theoretical concepts can get applied down the line. Graph analytics, time prediction. You could look at a graph and say, based on the cost of these edges that I've found before, I could go on and on. That's the idea. Is when you're based in these, so you get this secure grounding, but you get this wonderful space of knowledge to explore. And so, if there's one sort of takeaway here, that's my antidote to the the pessimism of this real operational feeling of everything is broken in a small way, and we've just layered on turtles, sad turtles on sad turtles. It's not all true, right? There are serious bodies of knowledge that people have been working to build, and if we can take stock, look for those bodies of knowledge, figure out a way to connect the complexity that we're trying to manage to existing areas of research, areas of practice. That's how we're gonna feel better after we read the sad server tweet, and we say, yes, everything is broken, but we can fix it. That's all I have for you. Thank you for your time. I look forward to seeing you at the conference.